The answer you got for this, what's wrong with this? Every time. Now, the answer you got for this, many of you got a slightly different answer than this here. Okay, so where did this answer come from? Or first you started with grams, methanol. You need to convert it to moles of methanol using the molar mass. Then, to go from moles of methanol to moles of water, you use the coefficient in the chemical equation. Then to get to grams of water, we use the molar mass of H2O. So your setup, many of you I checked already, you got approximately 32 grams of CH3OH. Many of you got a more precise value due to the periodic table you used, which was the correct AP1. And then the 4:2 ratio, and water's molar mass is approximately 18, but you may have used a more precise value. And many people got 235.03, something like that. 018. All right, so there's a little debate on that. We'll look at that tomorrow, how we can get exactly the same answer. If you're in that range, you did the setup correct. Now, if you look on the next page, this is another combustion chemical reaction. So how many grams of C2H2 are burned if the reaction produces 75.0 grams of CO2? So we'll give you about 3 minutes to look at this one. Try to set it up, calculate it out, and find your answer. Set it up. So in this problem here, we're looking at how many grams of C2H2 are burned. So our setup with our final answer written on the page. Grams to grams, to mole, to mole, to mole of the second substance, moles to grams. This one was one where you went from products to reactants. It doesn't matter which way you're going. The mole tunnel works both ways. Any questions on that? Now, one thing, I did see a couple people, you always want to use the molar mass. It makes life easier because then you can always you always go to the mole, then you always use the molar mass. It's always going to be per 1 mole. So that makes it really nice. This is always going to be a per 1 mole conversion factor. This will always be from the equation, and then this one is per 1 mole as well for the 26.036 grams of acetylene. Now, in chemical reactions, if you know how to look at a chemical reaction and determine its reactants and product amounts, the next thing to look at are 5 different types of reactions that we will focus on mainly in the course. First one is synthesis. Second one is decomposition. Third one is called a single replacement. Fourth one is a double replacement, and the fifth one is combustion, like we saw today. So the first type is synthesis. In synthesis, there are 2 or more things coming together to make a single product. Synthesis usually refers to make, so you're making one thing in a synthesis. So elements coming together to make a compound would be a synthesis, or elements and compounds coming together to make a new compound. It is a combination of 2 or more substances to form one compound. For example, chlorine gas is passed over a piece of sodium metal, producing solid sodium chloride would be a synthesis reaction. Yes?
For the second conversion, how come it turns into 2 ABCs? Like, where did the B2 and C2 go?
Okay, so the B2 and C2 here, what happened is there was a rearrangement of these hypothetical elements, and this 2 came out in front, so you have 2 A's now, 2 B's, and 2 C's all connected together. Whether this is actually a reaction or not You can have all sorts of different combinations, but that's just an example. And it came out in the front because it was a 1:1:1 ABC ratio in that formula. Now, second example is decomposition. That's A and B breaking up, or A, B, and C breaking up. And maybe they're not all breaking up differently. Maybe A and B stays together. That's a common decomposition reaction. So a compound is broken down into simpler substances, which usually requires energy. Usually requires energy for this to occur. So an example could be powdered ammonium dichromate is strongly heated. When you heat up a ionic compound, sometimes it can produce heat, nitrogen gas, water, and chromium 3 oxide. Would be one example of a decomposition reaction. Yes, sir?
Do you mean decomposition like dead body?
Yes, dead body decomposition is the same idea. The dead body is going from larger molecules or cells or tissue or the whole entire body, breaking down into its elements. So that's what happens. It doesn't just disappear, it just breaks into those elements.
Doesn't it give off energy like heat?
Yeah.
But
Yeah.
here it says it requires energy.
Yep, it requires energy to break down those bonds usually. Keyword here is usually. So it's an interesting thing. Well, where's the heat coming from? We'll learn about that when we talk about thermodynamics. The heat is coming from somewhere for the reaction to start. Once it starts, though, it might produce its own heat. It's possible. Good question. So this would be how to take the words of this equation and write it as a formula. From our equation writing, you know we could do this as of today. It's not easy, but that's something we can do at this point. Take the words and put them into an equation form. And then balance the equation, of course, to make sure it is a balanced chemical equation. Now, the next type of reaction is called a single replacement reaction. It's also sometimes called a single displacement reaction. This reaction here, the best example of this that I have, although there are tons of them, is the relationship between Bill Clinton and Monica Lewinsky. Now, once upon a time, there was Bill Clinton, and he was married to Hillary Clinton. And along came Monica Lewinsky. So we had Bill Clinton and Hillary Clinton together. And along came Monica Lewinsky. Now, you could probably invent this for almost any tabloid you want. Any person. Okay, Angelina Jolie, Brad Pitt, Jennifer Aniston, name anybody. Britney, somebody's. Okay, so as you see, what happened was Bill and Monica got together, and that left out Hillary to run for president. So, and then something else happened later on. But that's a single replacement reaction. Single replacement reaction, an easy way of remembering that if you like funny stories. So A plus BX equals AX plus B is a simple way of showing that, or you can just write out the Bill Monica Lewinsky if that helps you. One element is replaced by another in a compound. Yes?
Is that her real name?
Monica Lewinsky?
Yeah.
It was her name at one point. Don't know what she's done since then.
Isn't her name Marilyn Monroe?
Oh no, that was John F. Kennedy, I believe. We'll invent other ones at the end of the period for fun, okay? All right. It's okay. You don't need to know this for chemistry. You just need to know that. All right. The compound is usually an ionic compound. So if you had a piece of magnesium ribbon dropped into hydrochloric acid, it would generate hydrogen gas and aqueous magnesium chloride. Now, looking at this particular reaction, please finish the equation. I've written the first half of it for you. Please complete the equation and balance it. For magnesium ribbon being dropped into hydrochloric acid. All right, please raise your hand if you can tell me the first product. Yes, sir. H2. What phase is it? Gas. A little G down there. All right. Then what comes next? Yes, sir. MgCl. Okay. So we got two possible products. Any other possible products? You want Cl2. Why Cl2? Can you explain why, Lo Chan?
Magnesium has like a 2+ charge.
Uh-huh.
And Cl is 1-.
Uh-huh. Right, need two of those to make your compound. Magnesium chloride's got to be neutral. Now, once you have it neutral, what do the coefficients need to be? They're good only if you want to get it wrong. They're not good. There's nothing good about this right now with coefficients. There's something wrong, seriously wrong. Look at the left and right side. The formulas are right. The balanced equation is 100% wrong right now. Yes, sir. Thank you for your offer of truth. HCl on the left. Boom, that fixes it. Now we got two H's, two H's, two Cl's, two Cl's.
That's already on there.
Oh, but it wasn't on mine. Seriously, I didn't get it right. You guys were telling me it was right.
Oh.
Look at it. I mean, there was no 2 there. I mean, if I cross it out, is it now right again? No. All right. Now I know you're all like, well, but it said it was there. I know, it was there. You're right. So that should have been your balanced equation, obviously. Pretty easy to do. Now, the next one, called the double displacement, or double replacement, based on what you like. This one here also has a story to it. Once upon a time, there was a guy named Abe. And Abe was in love with this warrior princess named Xena.
Oh, wow.
And she was just really special. And his friend, Bob, he talked to his friend Bob and said, hey, Bob, why don't you ask out that girl over there who I don't know her name? And Bob was like, wow, that would be great. I think her name is Yasmin. So Bob asked Yasmin out, and Abe asked Xena out, and they went on a double date. And as they were at dinner eating some wonderful food, all of a sudden, Xena, the warrior princess, was not quite attacking Abe anymore, but looking at Bob. Bob was wondering, what do I do in this situation? I didn't know what to do. He was trying to be nice to Yasmin, but Yasmin wouldn't talk to him. So Bob decided he would talk to Xena out on the veranda, and that left Abe and Yasmin together. And everyone was happily ever after. Yes? What happened to who? Eva Longoria? I don't know who that is, but I'm glad it happened to her too. I hope she's okay. Alright. So that's a double replacement. This is a classic called double date reaction to keep it easy, but it is a very simple, logical, hey, you're left out in the cold, but in this case, you have a friend. So 2 elements or ions and 2 compounds are exchanged. Compounds are usually an ionic compound. One thing that means is the first one is usually positive, the second one is usually negative. So that means positive and negative cannot, positive and negative can go together, but not negative and negative or positive and positive. So don't try to stick 2 metals together in this type of reaction. It's not going to happen. So sodium iodide and lead nitrate. Oh, wait a minute. We've done this before, haven't we? Oh, yeah. Our fabulous favorite reaction. First day right here. That's a double displacement reaction, producing our solid product, precipitate, which is the lead iodide. All right? And our equation for that. Oh, did I give that to you? Am I supposed to? Uh-oh. Is it already there?
Yeah, it's already.
Not too hard to do. We've already practiced this. Don't need to practice it anymore. But that is a double replacement. Now, fifth type of reaction is a combustion, which we saw today. In a combustion, this setup is almost always correct, but sometimes there's an oxygen in here. So there's no O in your notes. So please write next to it, sometimes O is in the first thing. The CXHY refers to a fuel. Fuel combusts in presence of oxygen to produce carbon dioxide and water. This is a simple combustion reaction.
Wait, where did you say the O is sometimes?
Sometimes it's with the X and the C and the H in the first compound. So sometimes O is with everything in the reaction. Methanol is an example of that. CH3OH, it has H's, it has C's, it also has an O. Many liquid fuels have oxygen in them already. Gaseous fuels tend not to. Now, molecular oxygen combines with hydrocarbon, a hydrocarbon, which is the CXHY, to produce carbon dioxide and water. Hydrocarbon is composed of two elements. You can probably guess which two. It's pretty easy. Hydrogen and carbon. It always produces carbon dioxide and water. That's the nice thing about a combustion. If you know it's combustion, you already know your products and you know oxygen. So liquid ethanol is burned in air. Okay, to do this, the first thing we would need is the formula for liquid ethanol, which is C2H5OH, liquid. Then it's added to oxygen to produce CO2 and water. Once again, once we have the formulas written correctly, then we just balance it with the coefficients, and that's a combustion reaction. So this time we've done a lot of problem solving in here. What we can do right now is you're going to get started on your stoichiometry homework so that you can get as much of that done and you don't spend all night doing it. So, stoichiometry PS 1.03 in your lab manual or in your handout or in your printout. We're going to work on that right now. And just so you know, this is an ideal time. If anything is tripping you up, if anything's not making sense. We've got 15 minutes. I can spend 5 minutes with you, 3 minutes with you, 2 minutes with you. Go through any questions you have on anything so far. I am not assuming you know how to do anything, although you should know how to do everything. But if you don't, that's okay. It's better to know by the end of today than to be clueless. Stoichiometry is very easy if you know how to do all the other steps.